In this section, we'll be going over rational functions and how to graph them. So starting with the definition of a rational function is going to be a function which is a ratio or a fraction of polynomials. So there's going to be a polynomial in the numerator and a polynomial in the denominator, which means it'll be in the form f of x equals p of x divided by q of x, where p and q are both polynomials. So the domain of a rational function is going to be the set of real numbers, except the x values that make the denominator equal 0. And that's because we cannot divide by 0. So let's do an example with these domains. So let's find the domain of the following rational functions. So this first one, we have f of x equals x squared plus 7x plus 9 divided by x times x minus 2 times x plus 5. So the domain is going to be all real numbers except for when that denominator equals 0. So we have to set that denominator equal to 0 and solve. And when we set this equal to 0, since it's already factored for us, we can use that zero product property and say that if all three of these being multiplied together equals 0, then one of them has to be 0. So we set them equal to 0 separately. Set each factor equal to 0 and solve. So the first one's already solved, that's just x equals 0. Second one, we have to add 2 to both sides, so we get x equals 2. Third one, subtract 5 on both sides, we get x equals negative 5. So the domain here is going to be all real numbers except for x equals 0, x equals 2, and x equals negative 5. Okay, and I also wrote that in interval notation down below. So either notation would be fine for now. Okay, and doing another one here, we have g of x equals x squared minus 9 divided by x minus 3. So we don't have to worry about factoring, canceling common factors or anything when we're working with just the domain. So all we have to do is set this denominator equal to 0 once again, and solving this when it's set equal to 0, we have to add 3 to both sides and we get x equals 3. So that means the domain is going to be all real numbers except x equals 3. And once again, I wrote it in interval notation as well. That's negative infinity to 3, union 3 to infinity, which just means everything except for 3. And let's do one more here. So we have h of x is x plus 3 divided by x squared plus 9. So we set that denominator equal to 0 to see what we have to omit from the domain. And when we're setting this equal to 0 and trying to solve it, we would subtract 9 on both sides. We get x squared equals negative 9. We would take the square root of both sides, and remember you always get plus or minus the square root on this side. We would get x equals plus or minus the square root of negative 9. So this will end up giving us imaginary numbers because we have the negative underneath the square root. But since we're only interested in real numbers for these problems, since we're graphing them on an xy plane, this means that the domain is going to be all real numbers. And that's because the denominator will never equal 0, which should make sense if you take a look at it. X squared plus 9. X squared will always either be 0 or positive, so something 0 or positive plus 9 can clearly never be equal to 0. So in interval notation, that's negative infinity to infinity. Okay, so let's go over a couple what we call basic or parent functions with these rational functions. Starting with the first one, which is the reciprocal function. So the reciprocal function is f of x. F of x equals 1 over x. So let's take a look at the domain here. So the domain is going to be when that denominator is equal to 0. The domain is going to be all real numbers except for when that denominator is equal to 0, which is when x equals 0. So we can't plug in a 0 into this function because that means we're dividing by 0. So taking a look at the graph down here, we have the graph of f of x, which is 1 over x. So we can think of this, you can make a table of values if you want, and plug in values of x to get out its corresponding y value. So let's say we plugged in just negative 2, negative 1, 0, 1, and 2 real quick. If we plugged in negative 2, we would get 1 over negative 2, which is just negative 1/2. So taking a look at where that would be on the graph here would be negative 2 comma negative 1/2. That would be that point right here. If we plug in a negative 1, that would be 1 over negative 1, which would just be negative 1. Taking a look on the graph, that would give us this point right here. Plugging in a 0, that would give us 1 over 0, which we said we cannot divide by 0, so that would be undefined. So notice that at x equals 0, there's no curve going over x equals 0. So what's actually going on there is something called a vertical asymptote, which is just an imaginary line which we can denote with a dashed line. So it's not actually there, it's not actually part of the graph. It just represents essentially a vertical barrier that the curve will never cross through. And what this means as a vertical asymptote at x equals 0, which we'll get into a little bit more, it means that as x values approach 0, the function is either going to go towards positive infinity or negative infinity, which we can see that it does here because it shoots up right here and it shoots down over there. Okay, and then if we plug in a 1 here, plug in a 1 into f of x, f of 1 equals 1 over 1, which is 1, which is right here on the graph. Plug in f of 2, we get 1 over 2, get 1/2, and that would be right here. So those are just a couple examples. You can keep on plugging in values, and you would see that it looks like this curve after you connected them. So I'll just erase those. So one other thing that's actually going on here is a horizontal asymptote, which is at y equals 0, which is the x-axis, which once again we denote it with a dashed line. So notice how a similar thing is happening here as with the vertical asymptote. The function's getting closer and closer to it, which we call asymptotically approaching it over there and then over here on the left as well. And we'll get into both of these in detail in a little bit. Okay, for the next one we have the reciprocal squared function. So it's the function that we just had except squared. So this is f of x equals 1 over x squared, and the domain for this one is all real numbers except for the denominator x squared equals 0, which means x cannot be equal to 0 once again. Okay, so taking a look at this graph of it right here, you'll notice it looks pretty similar to the one that we just had, the reciprocal function, except instead of having the graph down here in the third quadrant, it gets bumped up into the second quadrant. Because of that squared, it makes everything positive instead of having it be negative. Okay, so I won't plug in a table of values. You can do that on your own if you want and get some xy ordered pairs out and graph them, but this is what it's going to look like. Once again, we have these asymptotes, and they're in the same location as before, vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. Okay, so let's get into these asymptotes a little bit more in detail here. So starting with vertical asymptotes. So vertical asymptotes is a form of a discontinuity. It's a line, but it's once again, it's not part of the graph, so it's kind of like an invisible line that the curve is going to get closer and closer to, but it cannot go through that line. So a curve can never pass through a vertical asymptote, and the kind of real definition of it here is the line x equals a is a vertical asymptote if f of x approaches positive or negative infinity as x approaches that a value. And just like I read it, that arrow means approaches or gets closer and closer to. And a function can have multiple vertical asymptotes. So let's see an example of this on this graph. Okay, so we have this curve here of f of x, and we can see that discontinuity over here at x equals a. So just pretend that's an x-coordinate, x equals a. And we can see that as the x values get closer to a from the left, so this way from the left, the function is getting bigger and bigger, which means it's going to infinity. And as we approach a from the right, So we go to the right of a and we approach the x values of a. F of x is approaching negative infinity. So this is how you could write it, and this little notation here is the way that I read it off. That means x approaches a from the left, and the plus means from the right. So f of x approaches infinity as x approaches a from the left. F of x approaches negative infinity as x approaches a from the right. So what that means is we have a vertical asymptote at x equals a. Okay, so the way that we find these when we have a function locating vertical asymptotes, we're going to simplify the expression. So after we simplify the expression, which means canceling common factors, which means we're going to have to factor, we may have to factor the numerator and factor the denominator, and then cancel those common factors. We're going to set the simplified denominator equal to 0 and solve for x. When we solve that for x, that's going to be our vertical asymptote. So let's do these examples here. The first one, let's find the vertical asymptotes. So we have f of x is x over x minus 3. So this is already simplified. So since this is already simplified, all we have to do is set this denominator equal to 0. And we solve that for x by adding 3 to both sides, and we get x equals 3. So that means there is a vertical asymptote at x equals 3. So I just drew it what we're going to be representing it with later on when we're graphing these, with just a dashed line, and we can denote it with a VA for vertical asymptote. So I'm not going to graph this yet. The actual function, we'll get into that in a little bit. Okay, next one we have f of x is x over x squared minus 4. So once again, this is already, we can't simplify this any further. We can try to factor it though. We can factor the denominator. That's a difference of squares factoring. That factors to x plus 2 times x minus 2. So we can't cancel any factors though. There's no common factors in the numerator and denominator. So all we have to do here is set that denominator equal to 0. So x plus 2 times x minus 2 equals 0. And we're going to set these equal to 0 separately based on that 0 product property. We set both factors equal to 0 and we solve them separately. We get x equals negative 2 and x equals positive 2. On the left hand side we had to subtract 2 on both sides. The right one we had to add 2 on both sides. So we just graph them over there on the graph. X equals negative 2 and x equals positive 2. Next one here, we have f of x is x plus 2 over x squared minus 4. So let's factor that denominator again, just like we did. Numerator can't be factored. Denominator is x plus 2 times x minus 2. So this time we have a common factor of x plus 2 that cancels, which means we're left with 1 in the numerator. So that's 1 over x minus 2. So now that it's simplified, we set the simplified denominator equal to 0, which is x minus 2, and that gives us x equals 2. Okay, so this time you got to make sure that you cancel off that common factor first, and we get x equals 2 as our vertical asymptote. So let's do one more here. We have f of x is x plus 2 over x squared plus 7x plus 10. So we factored this one, and this one factors to x plus 5 times x plus 2 in the denominator. So we had to think of two numbers that multiply to 10, that add to 7, and we see that the x plus 2's cancel, and we're left with 1 over x plus 5. Okay, so we set that simplified denominator equal to 0 once again, and we solve it for x, and we get x equals negative 5 as our vertical asymptote. Okay, so when we canceled out common factors, looking back up at this example that we just did, we still cannot plug in negative 2 into the original function because that'll make that denominator equal 0, but we canceled that factor off, which means it was not a vertical asymptote. What that's going to be is it's going to end up being what we call a hole. So a hole is another form of a discontinuity. We can call these removable discontinuities, and these are going to be points on the graph that the curve just skips right over. And when we graph it, we're going to place a hole at the spot where it skips over. And we call this a removable discontinuity because of the way that we canceled common factors. We removed the factors, and that's how we end up finding the holes. And just like vertical asymptotes, it can have function can have multiple holes. So for example, on this graph right here, we'll say we have this function. So notice here, there's this hole at x equals a. So if there's a hole here, that means the function does not exist at that point. So that means f of a does not exist. Or we can write that f of a is undefined. So notice how different this looks on a vertical asymptote. Vertical asymptote, the function's either going to positive or negative infinity, but with a hole, it just simply skips over that certain point and resumes the same pattern that it was doing beforehand. Okay, so for locating holes, when we are simplifying a rational expression, when we're canceling those common factors, instead of setting the simplified denominator equal to 0 like we do with the vertical asymptotes, we're going to set the canceled factors equal to 0, and we're going to solve that for x, and that's going to be the x coordinate where there is a hole. When we're graphing these, we're going to want to find the y-coordinate where the hole is. We can't plug it into the original because then we'll be dividing by 0. We're going to plug in the x value we found into the simplified version of the function. That'll give us the y-coordinate so we can just graph it accurately. Okay, so let's do these examples. Let's find the holes and the vertical asymptotes. So we have f of x is x minus 1 over x minus 1 times x plus 1. So this is already factored in the denominator, so we can go ahead and cancel that common factor of x minus 1 in the numerator and denominator, and that leaves us with 1 over x plus 1. So when we are trying to find the vertical asymptotes and the holes, for the vertical asymptote, we're going to set the simplified denominator, which is, here's the simplified version of the function. We set x plus 1 equal to 0. We solve that for x by subtracting 1 on both sides. So this, like we saw before, represents the line, like an invisible line, x equals negative 1. When we're trying to find the holes, we go to the factors that we canceled off, which is x minus 1. And we set that equal to 0 and solve for that one. We get x equals positive 1 after we add 1 to both sides. So this one represents an x coordinate. So even though they're both similar in the sense where they're discontinuities and they're both when the denominator equals 0, we find them just a little bit differently, and the x equals represents something completely different. Okay, let's do a couple other examples here. Let's say we have f of x equals x squared minus 9 divided by x plus 3. So first we are going to factor this numerator, its difference of squares, that factors to x plus 3 times x minus 3 over x plus 3. We can cancel common factors, x plus 3 over x plus 3. That leaves us with x minus 3 over 1, which anytime you have something over 1, you never have to write it. We're just left with x minus 3. So finding the vertical asymptotes and the holes. For the vertical asymptotes, we don't have anything in the denominator for the simplified version other than a 1. Since there's no variables left in the denominator, there are going to be no vertical asymptotes. For the holes, however, we canceled the common factor of x plus 3. So we set that common factor that canceled factor equal to 0, and we solve, and we get x equals negative 3 after we subtract 3 on both sides. So this time there was no vertical asymptotes, and there was a hole at the x coordinate of x equals negative 3. So if we wanted to find the y coordinate for this hole, we would go back and plug it into the simplified version, and we would get negative 3 minus 3, which would be negative 6, which would give us an xy ordered pair, negative 3, comma, -6. But we'll be getting into that when we actually graph these. Okay, so let's do one more here. We have f of x equals x squared minus 3x minus 18 divided by x squared minus 36. So factoring this numerator, we get x minus 6 times x plus 3, two numbers that multiply to -18, that also added to -3. Factoring that denominator, we end up with x plus 6 times x minus 6, difference of squares factoring for that one. And we see that x minus 6 will cancel. So we're left with x plus 3 over x plus 6. So there's our simplified version of this function. So now finding the vertical asymptotes and the holes. For the vertical asymptote, we go to the simplified version of the denominator, which is x plus 6. We set that equal to 0 and we solve for x. Subtract 6 on both sides. 0 minus 6, we get x equals -6. So there's a vertical asymptote at x equals -6. And then as for the holes, you go to the common factor that you canceled, which was x minus 6. You set that equal to 0. We add 6 to both sides to solve for x. We get x equals 6. So there is a hole at the x coordinate of x equals 6. Okay, so far that's vertical asymptotes and holes. Those are forms of discontinuities. Next, for horizontal asymptotes, just like vertical asymptotes, horizontal asymptotes are an invisible line, and these ones are obviously going to be horizontal. And the actual definition here is the line y equals b is going to be a horizontal asymptote if the function approaches that value of b as x goes to positive or negative infinity. So unlike vertical asymptotes, horizontal asymptotes can actually pass through horizontal asymptotes, and a curve can have at most one horizontal asymptote. So it may not have any, but at most it can have one. So let's take a look at this graph for an example. So let's say we have this function f of x, and we have this horizontal asymptote at y equals b. So that b is just some y coordinate, some arbitrary y coordinate. And notice that right here, I let the graph f of x actually pass through it just to represent that it can go through it sometimes. And notice that the function, as it gets closer and as it gets more to the right, which in this case means as x goes to infinity, the function seems to be flattening out right at y equals b. So we would say as f of x approaches b, or f of x approaches b as x goes to infinity, that means there's a horizontal asymptote at y equals b. So we could have done this the other way, or both ways, and said as x goes to negative infinity, or we could have had one going to on both sides, negative infinity and positive infinity. This one I just had it as x goes to positive infinity. So that is a horizontal asymptote. So for locating these horizontal asymptotes, what we're going to be doing is comparing the degree of the numerator with the degree of the denominator. And this is going to be of the original unsimplified function. So degree means the largest exponent in the numerator and the largest exponent in the denominator. So that's going to give us three options here. Either the numerator is going to be larger, smaller, or they're going to be equal. So let's start with the degree of the numerator smaller than the degree of the denominator. Anytime that happens, that means there's going to be a horizontal asymptote at y equals 0. So thinking about why this is, if the degree of the denominator is larger, as x goes to positive or negative infinity, that means the denominator is going to get larger a lot faster than the numerator. And if the denominator is getting larger than the numerator, a large denominator means the number as a whole is very small. So that means the number as a whole would be going to 0, so y equals 0 for a horizontal asymptote. So let's say that the degrees are equal. Degree of the numerator equals the degree of the denominator. Whenever that's the case, there's going to be a horizontal asymptote at y equals, it's going to be a ratio. It's going to be y equals the leading coefficient in the numerator divided by the leading coefficient in the denominator. So it's going to be the number multiplying the highest degree in the numerator divided by the number multiplying the highest degree in the denominator. And lastly, if we have the degree of the numerator larger than the degree of the denominator, that means there's going to be no horizontal asymptote, but notice I put there may be a slant asymptote, which we'll get into in a minute. Okay, so let's do 3 examples here. First one, we have f of x is 4x over 2x squared plus 1. So all we have to do here is look at the degree in the numerator and the degree in the denominator, so the largest exponents here. And we notice that the degree in the numerator is 1 because that is the exponent on the variable, and the degree in the denominator is 2 because that's the exponent on the variable. So the degree in the numerator is less than the degree in the denominator. Anytime that happens, we know there's a horizontal asymptote at y equals 0, which is the x-axis. And just like vertical asymptotes, we can abbreviate when we're graphing it. I abbreviate horizontal asymptotes with HA. Next one, we have f of x is 4x squared over 2x squared plus 1. So we look at the highest degree in the numerator and denominator. So we have this x squared term and this x squared term. So they're both degree 2. So the degree in the numerator is equal to the degree in the denominator. And whenever this happens, that means we have a horizontal asymptote at the ratio of the leading coefficients. The leading coefficients here are going to be this 4 and this 2. So that means our horizontal asymptote is going to be at y equals 4 divided by 2, which obviously simplifies here to y equals 2. So on the graph, that's going to be just at y equals 2, a horizontal dashed line. Last one here, we have f of x equals 4x cubed divided by 3x squared minus x. So taking a look at these degrees, numerator and denominator, we have x cubed in the numerator, x squared in the denominator. So degree 3 in the numerator is higher than degree 2 in the denominator. So that means there is no horizontal asymptote. Okay, so I'm just going to leave that graph blank over there. Okay, so those are the only 3 options for having a horizontal asymptote. So before we get into kind of the last thing, let's determine if the function crosses a horizontal asymptote, because remember it can cross a horizontal asymptote. So to determine if it does cross at the horizontal asymptote, we're going to find the horizontal asymptote first, and then we're going to set the simplified version of the function equal to that value that we found and solve it for x. If we can solve for x, then we know it crosses at that point. If the variables cancel completely, then that means it never crosses the horizontal asymptote. Okay, so let's see this example right here. We have f of x equals 4x over 2x squared plus 1. So we notice that the degree in the numerator is smaller than the degree in the denominator, which means we have a horizontal asymptote at y equals 0. And what this means is that we are going to set f of x equal to 0 and solve for x. Okay, so I'll do that up here. F of x equals 0. That's going to be 4x over 2x squared plus 1 equals 0. So anytime you have a rational expression equals to 0, you would try to factor it, and then you cancel common factors. You set the simplified numerator equal to 0. This one does not have any factors to cancel, so this is already simplified. So we set this simplified numerator equal to 0. So we get 4x equals 0. Divide both sides by 4. That gives us x equals 0. So that means since we actually could find a value here, since we actually solved it, that means it crosses the horizontal asymptote at x equals 0. Since the horizontal asymptote was at y equals 0, that's how we knew that that was the y coordinate. Okay, so let's do one more here. So we have 4x squared over 2x squared plus 1. We recognize that the degrees are the same in the numerator and denominator. So that means the horizontal asymptote is at the ratio of their leading coefficients. Horizontal asymptote at y equals 2. So we're going to set the function equal to 2, and then we're going to solve for x. So I'll do that up here. We're going to set f of x equal to 2. And that's going to be 4x over 2x squared plus 1 equals 2. So this one we have to cross multiply or multiply both sides by 2x squared plus 1. So that means we have to multiply 2x squared plus 1 to the right-hand side of the equation. So we get, oops, I forgot the squared up here. 4x squared equals 2 times 2x squared plus 1. And we distribute that 2 on the right. We get 4x squared plus 2. We would try to subtract, to get the x's on the same side, subtract 4x squared to the left-hand side. However, it actually cancels off on both sides. So we're left with 0 equals 2. So since this time the variables canceled and we clearly have a false statement here, 0 equals 2, that means it never crosses the horizontal asymptote. Okay, so variables completely cancel, then it never crosses the horizontal asymptote. Okay, so for the last thing here before we get into actually graphing these now are the slant asymptotes. So a function can have a slant asymptote, so it's just like horizontal vertical asymptote except on a slant. If only on one condition here, and that's if the degree of the numerator is 1 more than the degree of the denominator. And just like a horizontal asymptote, a curve can pass through a slant asymptote. So let's see what this looks like on this example. So it might look something like this. I threw in a vertical asymptote for this one also. So you clearly can see this slant asymptote right here, and the function approaches it as it goes this way over here and to the left over here. Okay, so to find these slant asymptotes, what we're going to have to do is use long division or synthetic division to divide the rational expression. And the slant asymptote, when we're doing the division and we're finished dividing, is going to be the quotient. So the quotient, or the answer essentially, is going to be the equation of the slant asymptote. The only thing we have to look out for here is if the remainder is equal to 0, then there is no slant asymptote. If the remainder is 0, the function itself is what the slant asymptote would be. Okay, so let's do this example here. Let's determine the slant asymptote. So we have f of x squared plus 1 divided by x minus 1. So the degree of the numerator is 1 more than the degree of the denominator, so there may be a slant asymptote. So we're going to divide. So we're going to divide this. I'll use long division here. So it's going to be x squared plus, I'll throw in a 0x because there wasn't an x term, just so it lines up nicely. And this is going to be divided by that denominator of x minus 1. So remember, we can divide these leading terms to help us. We're going to end up getting an x here, multiply that through and subtract. We get x squared minus x. And then we subtract this. The x squareds cancel. 0x minus a negative x is positive x. Bring down that plus 1. And then we can have a 1 right here. 1 times that divisor, we end up getting x minus 1. And we subtract, we get 1 minus negative 1, which is 2. So the remainder is not equal to 0, so we do have a slant asymptote. And the slant asymptote is right up here, which is the quotient. So there's a slant asymptote at y equals x plus 1. So this was actually the function right up here that I graphed. And notice that this line right here for the slant asymptote is y equals x plus 1. Okay, so that only can happen if the degree of the numerator is 1 more than the degree of the denominator, which means numerator, larger degree than denominator, no horizontal asymptote, but maybe a slant asymptote. So you can see how we can't have both of them at the same time. Okay, so before we get into using everything we just did to graph these rational functions, let's do 2 quick examples using transformations just to remember how to do this using transformations. So to do this, we're going to base them off of the basic functions from this section and use the same transformations as before. So let's graph this first one. We have g of x is 1 over x minus 2 squared plus 1. So this basic function here, we have to take a look at this g of x. Our basic function from this section is either going to be the reciprocal function or the reciprocal squared function. Since there is the squared here, it's going to be the reciprocal squared function, which is 1 over x squared. So we're going to graph that out. So I'm just doing a rough sketch for this one. So that one looks something like that. And then zoom in a little bit, for the next thing, what we have to check if there is a horizontal shift, which there is. And the horizontal shift is going to be to the right 2 units because it's x minus 2. So graphing this to the right, it's going to look like this. And when it gets moved to the right 2, notice that the vertical asymptote gets moved to the right 2 as well. So the vertical asymptote's now at x equals 2. And for the last thing here, there's no stretching or shrinking, there's no reflection. There's this plus 1, which is a vertical shift up 1 unit for this last step. And we're going to base that off of our step 2 graph, so we're going to move everything up 1 unit. And our graph would look something like this for g of x. So notice that the horizontal asymptote got moved up 1, so it's now at y equals 1. Okay, so let's do one more here. So we have h of x is 1 over x plus 3 minus 2. So we're going to start with the basic function. And the basic function here is the reciprocal function. It's 1 over x because there's no x squared down there. So we graph this basic function, once again, pretty rough sketch for it. We have the horizontal asymptote and the vertical asymptote. And the next thing we look for is the horizontal shift. And there is a horizontal shift. It is going to be to the left 3 because it's x plus 3. So graphing that out. And that'll look something like this. So notice that the vertical asymptote got moved to the left 3 units. It's now at x equals negative 3. And lastly, there's no stretching or shrinking, no reflection, but there's this vertical shift minus 2. So we're going to move everything down 2 units for this last one. So the final version of the graph will look like this after that vertical shift. And notice the horizontal asymptote got moved down 2, so it's now at y equals negative 2. Okay, so those were examples where we could use the transformations. We won't always be able to use transformations, however, so we'll do about 5 examples here of graphing rational functions, and we'll be doing it in these steps. So the first step for graphing rational functions is going to be find the y-intercept. So y-intercepts are going to be evaluating f of 0. So it crosses the y-axis when x is 0, so that's why we evaluate f of 0. Second step, we're going to find the x-intercepts, and we do this by setting the function equal to 0 and solving for x. And what we have to do here is set the simplified numerator equal to 0. So after we cancel common factors, if we can do that, we set the simplified numerator equal to 0. Step 3 is going to be locate the vertical asymptotes. 4, locate any holes. Step 5, locate horizontal asymptote and determine if it crosses it. Step 6, locate a slant asymptote, if any. And step 7, which we'll see how we decide to choose some points here. We're going to plug in some values of x to find its corresponding y value and plot those points on certain intervals, and then we're going to connect it with a smooth curve with arrows on the end. And a couple notes here to keep in mind. A rational function can have multiple vertical asymptotes or none, multiple holes or none, at most one horizontal asymptote or a slant asymptote, but not both. And we're going to use the simplified version of the function to help us graph it. So what I do to start these is I always simplify and cancel common factors before I do anything. Okay, so let's do a couple examples here. So let's graph the function 2x minus 1 over x minus 1. So this is already simplified. We can't factor and cancel any common factors. So we can go ahead and find the y-intercept. And we know that this is going to be evaluating g of 0. So we're going to plug in a 0 everywhere there's an x. So it's going to be 2 times 0 minus 1 over 0 minus 1. So this is going to end up giving us negative 1 over negative 1, which is positive 1. So we know there's going to be a y-intercept at the coordinate 0, 1. And for the next thing, we can find the x-intercepts. So there could be 0 x-intercepts, there could be multiple x-intercepts. So we're going to take the function and we're going to set it equal to 0. So we're going to take g of x, set it equal to 0. So that's going to be the whole function equal to 0. So when we are trying to do this, we have to remember what we said on the previous page. We set the simplified numerator equal to 0. Since we couldn't cancel any factors, this is simplified, so we set this numerator equal to 0. And we solve this for x, so we would have to add 1 to both sides and then divide by 2. We would get x equals 1/2. So this would give us the coordinate 1/2, 0 for our x-intercept. And for the next step, we have to find any vertical asymptotes. And we do this by setting the simplified denominator equal to 0. So we just set that denominator equal to 0. We solve for x, and we get x equals 1 as our vertical asymptote. So that's the vertical line at x equals 1. And for the next step, we're going to find any holes. But we know there's no holes because we weren't able to cancel any common factors, so there's no holes. So next step is horizontal asymptotes. So we have to compare the degree of the numerator with the degree of the denominator. So those are both degree 1 in the numerator and denominator. So the degrees are equal. So that means there's a horizontal asymptote at the ratio of the leading coefficients, which, taking a look up here, the leading coefficients are 2 and 1. So there's a horizontal asymptote at y equals 2 over 1 or y equals 2. And to determine if it crosses it, what we would do is we would set the function equal to 2. So we would set the function equal to 2, and then we would try to solve for x. What we would find is that the variables cancel off, and when the variables cancel off, that means that it never crosses the horizontal asymptote. So it never crosses the horizontal asymptote. And then for the sixth one, for slant asymptote, we know there's no slant asymptote because we already have a horizontal asymptote, and the degree of the numerator is not greater by 1 than the denominator. So before we plot some points here, let's graph what we have so far. So we have the y-intercept at 1, the x-intercept at 1/2, and we have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 2. Okay, so that's about all we have right there for these for the information for this graph. So let's plot some points here. So we don't have any information on this whole side of the graph. So let's pick x coordinates over there and plug them into our function to see where the graph is. And let's also pick maybe one more x coordinate over here. Okay, so I chose -2 and 2 and 4 to plug into the function, and I didn't show my work, I just evaluated it from the original function. So g of 2 is 5/3, so that gives us a xy ordered pair, -2 comma 5/3, maybe about right here. And then we have 2 comma 3, which would be right here, and 4 comma 7/3. 7/3 is a little bit more than 2, so that would be about right here. And that's actually enough to graph it, even though it doesn't look like it. We have to fill in the rest by knowing how the graph behaves at the asymptotes. So it would have to look something like this. Okay, so for the next one here, we have f of x is x squared minus 4 over x minus 2. So let's simplify this right away. So we can factor that numerator to x plus 2 times x minus 2 because it's difference of squares factoring. And then we recognize that the x minus 2's can cancel. And we're left with x plus 2 over 1. So that's just x plus 2. So what we should recognize here is that our graph is going to look like the graph of x plus 2, which is linear, so we should know how to graph that, except it's going to have a hole when x minus 2 equals 0. So I'll run through this one pretty quickly. Evaluating the y-intercept, plugging in a 0 into x, f of 0 ends up being 2. So just be a little cautious. Always plug it into the original equation just in case there ended up being a hole at that point. So next, for the x-intercept, we set the function equal to 0, which means we set the simplified numerator equal to 0, which is x plus 2, and we get x equals -2 for our x-intercept. And now for any vertical asymptotes. We know that there's no vertical asymptotes because the denominator in the simplified version is just 1. The denominator canceled, so there's no vertical asymptotes. For the horizontal, or for the holes rather, for the holes we're going to set the canceled factor equal to 0 and solve it. So the factor that we canceled was x minus 2. So we set that equal to 0 and we get x equals 2. So what I'm going to do here to find the y-coordinate where the hole will be, I'm going to plug it into the simplified function, which ended up simplifying to x plus 2. So I'm going to plug in 2. I'm going to plug in the x-coordinate of the hole. So that gives us 2 plus 2. So that gives us f of 2 is 4. So that gives us a hole at the coordinate 2 comma 4. And for the horizontal asymptote, we have to take a look up at the degree in the numerator and the degree in the denominator. The degree of the numerator is 2, degree in the denominator is 1, so the degree in the numerator is larger, so there's no horizontal asymptote. And lastly, for the slant asymptote, there could be a slant asymptote. However, if we divide the numerator divided by the denominator, we're going to end up getting a remainder of 0, which means there's no slant asymptote. Okay, so let's graph what we have so far here. We have the y-intercept at 2, x-intercept at -2, and a hole at 2 comma 4. So since we know this is going to be linear with that hole because it simplified to a linear function with a hole, we can just connect that as a straight line. And that is our function f of x. So that one actually ended up being linear with just a hole in it. Okay, so for the next one, I'll keep on doing these a little bit quicker here. So the next one, we have x minus 4 over x squared minus 16. So we can simplify that denominator as x plus, or we can factor it as x plus 4 times x minus 4. And we have a common factor of x minus 4 in the numerator and denominator. So they cancel, and we are left with 1 over x plus 4. So if I were doing this, I would recognize that this is going to be a transformation of the reciprocal function 1 over x. It's going to be a horizontal shift to the left 4 units, and we have to take into account the whole. But let's do this the way that we've been doing it. So for this y-intercept here, we get a y-intercept of 1/4. And next for the x-intercept, we have to set the function equal to 0, which ends up being the simplified numerator. The simplified numerator is just 1 after the common factors cancel. So we're actually left with just 1 equals 0. Since there's no variables here and we have a false statement, that means there's no x-intercepts. Okay, next for the vertical asymptotes, we set the simplified denominator, which is x plus 4. We set that equal to 0. So we get x plus 4 equals 0. Solve it for x. We get x equals -4 when we subtract 4 on both sides. So there's our vertical asymptote. And now for any holes, we set the canceled factors equal to 0. So we canceled the common factor of x minus 4. So for setting that equal to 0, add 4 to both sides, we get x equals 4. And just like last time, I'm going to plug this in to the simplified version of the function to find its y-coordinate. So we're going to plug that into 1 over x plus 4, so f of 4 is going to be 1 over 4 plus 4, which gives us 1 over 8. So that's the xy ordered pair for the whole, 4 comma 1/8. And for the horizontal asymptotes, we have to take a look at the degree of the numerator and denominator. The degree of the numerator is 1, degree of the denominator is 2. So the degree of the denominator is larger, so there's a horizontal asymptote at y equals 0. And once again, technically we should check if it crosses. So you would set the function equal to 0 and try to solve it for x. You would see that the variables cancel once again. And you just end up getting the numerator, the simplified numerator, equal to 0, which is 1. So you get 1 equals 0, which is a false statement, which just means it never crosses the horizontal asymptote. And we know that there is no slant asymptote because we can't have both horizontal and a slant. And lastly, let's actually plot what we have so far, and then we'll see what points we can plug in to help us. So let's plot down this y-intercept of 1/4. There's no x-intercept, and the asymptotes, and the whole. Okay, so this is what we have so far. So let's plot some extra points here. So it looks like we don't have any x-coordinates over here on this side of the vertical asymptote. So let's pick maybe 1 or 2 over there. And then maybe let's pick 1 more over here. It doesn't really seem like we need it, but let's just do it anyway. Okay, so the points that I picked over here for plotting these points, I picked -5 and -2 to plug in. And I got h of -5 is -1, h of -2 is 1/2. And just a side note, if you noticed, I just changed this over here to h of x. I had it as f of x, but our function is called h of x. Okay, so plotting these points, we have -5, -1. That's going to be right here. And then we have -2 comma 1/2, which is going to be right here. So hopefully it's pretty clear that this is enough to graph it on the right side of the vertical asymptote, and it'll look something like this. Kind of has to look like that based on the behavior at the asymptotes, and we know it never crosses the horizontal asymptote. On the left-hand side of the vertical asymptote, once again, there's only 1 point over here, but we know the behavior at the asymptotes, so we know that it has to look like this. Okay, so you could plug in more points if you want to verify that, but that is definitely enough to help us graph it. Okay, so a couple more here. So x squared minus 4 over x squared minus 7x plus 10. So first, let's factor this. The numerator is difference of squares. which factors to x plus 2 times x minus 2. The denominator is a trinomial quadratic, two numbers that multiply to 10 that add to -7 are going to be -5 and -2. So that factors to x minus 5 times x minus 2. The x minus 2's cancel, and we're left with x plus 2 over x minus 5. Okay, so I'm going to run through and just fill in the y-intercept, x-intercept, and vertical asymptote real quick. Okay, so our y-intercept is going to be at -2/5. Our x-intercept is going to be at -2, 0. And I threw in a little ... here just to represent that jump from setting the function equal to 0 to setting the simplified numerator equal to 0. So we got the x-intercept at -2 and this vertical asymptote at x equals 5. Okay, so next I'll just fill in the holes and the horizontal asymptote / slant asymptote. So we have a hole at x equals 2, which gives us the coordinate 2, -4/3. Horizontal asymptote at y equals 1, which is the ratio of their leading coefficients because the degrees were equal. And there's no slant asymptote. So let's graph down what we have here. So this is what it looks like when we plot everything that we have. Hopefully the left side of this vertical asymptote is pretty obvious. We should know it looks something like this. And for the right-hand side of the vertical asymptote, let's plug in an x value to the right of 5 and get its y value out just so we can verify that it's up here. Okay, so using the points, the x coordinates 6 and 8, I got f of 6 equals 8 and f of 8 equals 10/3. So we can plot those down here. So we got those 2 points, and now we can just connect them similar to how this usually looks. And this is our graph of our function f of x. Okay, the next one, once again, I'm just going to fill out the y-intercept, x-intercepts, and the vertical asymptotes. So just notice that this cannot be factored. The numerator is not difference of squares. There's an addition sign, so we cannot factor it that way. So for the y-intercept, we get 0, -1. We get the y-intercept at -1. For the x-intercepts, setting the simplified numerator equal to 0, we actually end up getting plus or minus the square root of -1 when we solve that for x. So the square root of a negative implies imaginary numbers, which means there's no x-intercepts here. And then for vertical asymptotes, we set the denominator x minus 1 equal to 0, and we get x equals 1. Okay, next for the holes, horizontal asymptotes, and slant asymptotes. So for the holes, we didn't cancel any common factors, so there's no holes. Horizontal asymptote, there's no horizontal asymptote because the degree of the numerator is larger than the denominator. But for a slant asymptote, the degree of the numerator is 1 more than the degree of the denominator. So there could be a slant asymptote. So we check by doing long division. And we divide numerator divided by denominator. We get a quotient up here of x plus 1. And we get a remainder that is not equal to 0. So that means our slant asymptote is y equals the quotient, which is y equals x plus 1. So let's graph everything we have here, and then let's see what points we have to plug in. So this is the information that we have so far: slant asymptote, vertical asymptote. So if you wanted to double check to make sure the function never crossed the slant asymptote, what you could do is set the function equal to the slant asymptote, set it equal to x plus 1, and then you would try to solve for x. You would see that the variables cancel off, and you have a false statement, which means it never crosses the slant asymptote. Okay, so for some points here that it looks like we can plug in. So hopefully it's actually pretty obvious what's going on down here. There's only one shape that it can look like. We'll plug in a point down there though, and let's plug in points to the right of the vertical asymptote, and then we can see what's going on over there. So I use the x coordinates of -3, 2, and 4, and I found h of negative 3 is negative 5 over 2, h of 2 is 5, and h of 4 is 17 over 3. So let's graph them. Negative 3 comma negative 5 halves would be about right here. Negative 5 halves is negative 2.5. And for 2 comma 5, that would be right up here. And for 4 comma 17 thirds, that 17 thirds is a little bit more than 5, a little bit less than 6. It's 5 and 2 thirds. So now we can connect these, and it should look something like this. Okay, and that is our function h of x. Okay, so let's do one more here, and I'm just going to I'll pause the video and fill out everything for it, and then we'll discuss the graph afterwards. The reason is this one gets a kind of funky here. Okay, so when we factor this one, there's actually no common factors to cancel, so it's a little bit messier. So we have a y-intercept of negative 6, an x-intercept, we have two of them. We have negative 3 and negative 2. We have two vertical asymptotes, negative 1 and 1, x equals negative 1 and x equals 1. And there's no holes because we didn't cancel any common factors. The horizontal asymptote is y equals 1 because the degrees were equal. This one was a little bit different, again, because this one actually crosses the horizontal asymptote. If you took the function and you set it equal to the horizontal asymptote and you solved it for x, you would end up getting x equals negative 7 over 5. So it crosses the horizontal asymptote this time, and there's no slant asymptotes because there is a horizontal asymptote. So I plotted down all of the stuff that we found out here. I plotted all of the two vertical asymptotes, I plotted the horizontal asymptote, I plotted where it crosses the horizontal asymptote, I plotted the x-intercepts and the y-intercept. So it looks a little bit different here. So let's see kind of what we need here to fill this in. So we need some points to the right of this vertical asymptote because we don't have anything plotted there. So for that one, I used f of 2. And I also wanted another point over here somewhere to see what's going on, so I used negative 5. So I evaluated these. F of negative 5 is 1/4. F of 2 is 20 over 3. So let's plot those right now. So f of negative 5 is 1/4. And f of 2 is 20 over 3, which is a little bit more, or it's about 6.7-ish. Okay, so let's graph this right-hand side. The right-hand side, pretty much only one main thing can be happening here. And then if you didn't believe me, you could go ahead and graph or plot another point over here. Maybe choose x equals 6 and plug that in also, but it's going to look something like this. And I did throw in one extra point. I just plugged in 6 into the function and got about, it's a little bit more than 2, so I just plotted that point for accuracy. So for the middle portion here between the vertical asymptotes, there's actually only one thing it can look like. It has to look like this. So kind of hard to see, but it looks something like that, kind of like this, almost parabolic, but not a parabola. And I kind of cheated a little bit. I knew that it went up to here for the max. Don't worry too much about that. But we knew it had to look like that and go down on both sides, because if it went up, that means it would have to cross the horizontal asymptote and cross the x-axis. But we knew that we didn't find those points when we did these calculations, so it just has to go downward. Okay, so now for the points on the left here, it has to look something like this, because it has to go up to following this vertical asymptote, and then we knew it crosses the horizontal asymptote right here. It has to cut through both of these x-intercepts, and the only way to do that is to go through the one and then come back through the other one. And then based on this point that we plotted right here, we know that it has to go through that, and then it's just going to asymptotically approach that horizontal asymptote as x goes to negative infinity. Okay, so definitely a lot more complicated for that one. but that is our function f of x, and that's it for this section.